Next experiment in our control system is in the previous laboratory. We just gone through about the root locus. What is the equation? What is the program for that? In the same way, we will learning two more concept where it is analyzed that the stability of any of the system is going to be measured. The analysis what it is done in two more ways we can find out of that. That is about a Bode plot and also about a Nyquist plot. How this all be going? We'll go through the here. We know that what is the frequency response, where we'll be getting the equation in terms of a numerator and denominator part. Here, the magnitude of the frequency response is represented as m of omega, and phase frequency response is taken as pi of omega. I can represent the magnitude of any of the given system as m of omega is going to be based on the zeros and poles, actually m of o of omega and divided by m of I of omega. I can write here. And in terms of frequency response also, pi of omega, O of real and imaginary parts in such way will be going to be minus of pi I of omega. Next, when I'm going to be taking any of the equation it is given in terms of the numerator part and in denominator part, where the equation it is, if it is in terms of a j omega, means where we are going to be converting the transfer function by applying a Laplace transform. The transfer function of a Laplace form can be changed into a frequency response just by replacing j omega as s, where instead of j omega I can write here as s. Whatever the expression, if I'm writing in terms of s, means where I converted the equation to a Laplace form, where it is giving the information about in terms of a frequency. Next, it is similar to a Z transform, where we are converting from time to frequency time. Here also the same thing. The plot of frequency response, it is in two ways. That is the function of frequency with the separate magnitude and phase plot, and also about a polar plot. Next, magnitude and phase plot is nothing but our Bode plot, where we are going to represent the magnitude in terms of 20. That is where dB, that's going to be representing decibels. In some of the examples in AC, you will be writing 3 dB cutoff and 4 dB to cutoff minus of some values, right? The same thing here it is going to be. The dB, it is representing a 20 log m, 20 log m of the magnitude part, and a phase curve or a phase angle versus the log omega, we have to go with that. Then data for plots can be obtained using the vector and the S-plane drawn from the poles and zeros in the imaginary axis. This is the example where it is shown here. We are going for, there are two zeros and two poles in the equation. Then the magnitude response at a particular frequency is going to be taken as the product of the length of from the zeros of G of S divided by the number of vector length of the poles. Means zeros to poles, I can go with that. Then the angle of these is taken as here for zeros T1, theta1, theta2, and for poles theta3, theta4. That therefore the total angle what I will be getting is of the total number of zeros minus the total number of poles. Theta1 plus theta2 minus theta3 plus theta4 you will be getting off. Just an example here it is taken, where it is the equation given for us. J omega is going to be given as 1 divided by j omega plus 2. Where what I first step we have to do is, instead of j omega, I have to substitute add s. Before that, it is given a taken as a complex conjugate of this. Then it will be as a 2 minus j omega, or else minus j omega plus 2. You can write it off. Then if you solve for this, you'll be getting as 2 minus j omega divided by omega square plus 4. Then from that equation, you have to find what is the magnitude part. What is the magnitude? I can find out square root of the g of j omega of a real part and also of the complex conjugate part. Observe here, it is taken here. Now I'll be getting the magnitude part is going to be 1 divided by square root of omega square plus 4. I'll be getting out. Then in terms of finding the angle, that is equation is going to be minus tan inverse of b by a, imaginary to the real. The same way we have to go with 2 minus j omega. First you have to observe whether in the numerator or else in the denominator is there any imaginary term. If it is having the imaginary term, then I can write it off the equation in terms of say what is the angle. If it is not having this, we can tell that it's a zero angle. Means in the denominator part, it is not having any imaginary value. For that reason, we can't going for the finding of the angle in the denominator part. Only in the numerator part, we have the imaginary value, that is minus j omega. Therefore, what is the phase is going to be pi omega. That's going to be minus tan inverse omega by 2. Based on the magnitude and also of the phase, we have going to be for different values of omega with the frequency. I can substitute for 0, 1, 2, 3, depends on the which problem, which applications we are going to be using. Those values we have to substitute, and what is the angle and what is the magnitude we will be getting, we have to note down of those. Then when I plot a graph, this is the Bode plot we call. This Bode plot will be giving the magnitude plot and also about the phase plot. This is the magnitude plot, what we will be getting by of this equation. What it is given, 1 divided by j omega plus 2. And the phase angle is of representing like this. You'll be having the calculation methods, how we will be getting each and every values. I'm not going to deal with those. In the theory classes, I hope you learned of those. This is the polar plot only of the angle where I can go with the plotting. In the same, it's going on for one more example. Just you have to go with the complex conjugate. Take the numerator and denominator part, then go for magnitude and phase angle, what you will be getting, then plot the graph. This is your Bode plot diagram. Next, in terms of a Nyquist, if I am going for this Nyquist plot, it relates the stability of a closed loop system to the open loop frequency response and to the open loop pole location. This Nyquist plot, it is exactly giving the information about whether the poles are where it is placed and the stability of the pole, whether it should be a properly one or not. This Nyquist criteria is very much similar to the root locus, but the way of conveying the information is different compared to the root locus. When we go with in a general way, which one is easiest method? It's preferring for Nyquist only, but the Nyquist is not giving the exact stability of the function. For that reason, we preferring, while finding any of the system stability, we preferring for the root locus only. It's some of the textbook. It's given based on that. I'm telling it's you can go with a different textbook. They will be opening different theories and different researchers who explaining their own way. It will be different, but as per my knowledge, root locus will be giving much more information about the stability comparing with these two, but these two will be applicable in different applications, which method will be useful. I don't tell all root locus only will be given the exact value, but I can prefer with going with the root locus only. Then Nyquist criteria, it is mapping counter which is going for where it is locating, in which quadrant, in which way it is going to be representing. Those will be giving the information in the S plane and also in terms of a F plane. The pole where it depends on the where is the pole is located. These are different contours will be going for where it is changing. Observe here, it's for pole. Here it is different. For F plane, it will be different. And 0. And for pole, again, here in the F plane, it is be in a fourth quadrant. Here it is going to be second quadrant. You'll be going with the analysis in a theory classes. After this theory class, I can go with one more time. Here, when checking the stability of a system, the shape of the counter that we will be using, the counter is of a encircling the entire right half of the plane. This is how basic you should know about a Nyquist plot, where it is going to be taking a path in this way, half of the encircled it towards the right side. Then the number of closed loops in the right half of plane, that are going to be equals to 1 plus j of h, and that's going to be equals to 0. And open loop poles, that is towards the right half side, that is p. Then the counterclockwise rotation, if I go with minus 1 comma 0, then it's giving the number that is going to be n is going to be p minus z. This relationship is going to be called as a Nyquist criterion, And mapping through G of S through H of S is called as a Nyquist diagram. Here some of the examples given, where observe here, where here it is of 3 poles are located and 2 zeros are located here. Wait, for this, your Nyquist criteria is going to be taking this path. Then P is going to be equals to 0, N is going to be equals to 0. Then Z is going to be equals to P minus N is going to be equals to 0. If I am going to get this value, then I can tell that system is of a stable one. Observe here, the Nyquist plot, what will be getting for this condition? Here it will be like this. First path will be finding of this, and then you'll be getting the path like this. Then one more, consider here the imaginary. Observe here the number of zeros are towards your right hand instead of left hand. But from the root locus, we telling that our poles and zeros should be lie on the left half of the S plane instead of right half of the S plane. For that reason, in this case, the what you'll be getting, observe in both diagrams, where our -1 is located here. It's not encircled with a -1, but here our -1 is encircled based on the poles and zeros. Therefore, this system we are calling as a unstable system, where Z is going to be equals to 2. 0 minus of -2 is going, N is going to be equals to -2. Therefore, 0 minus of -2 is going to be equals to 2. Therefore, the system is of a unstable. This is stable one and this is of a unstable one, where our 2 zeros are located towards the right side. Here in this case, all are lying in the left hand side. Based on that, we have to tell. That's what here the information giving us. Next, this is just sketching how we are going for a Nyquist criteria. Based on the steps are there, we can go through of that. This is one example is given, a Nyquist diagram based on the block diagram, where we have a value actuators, a controller is there, a turbine, means a rotating element we are going to be taking here, and the generator, a sensor. Whatever the error is there, we can feed back that error to the controller, and again it's changing the position, how much value has to be taken place. Here a diagram based on this, where desired speed, how much the motor should rotate, or else your turbine is here in this example it is taken. The value of amplifier, valve actuator, and steam value, it's going to be 100 by S plus 10, and steam pressure is going to be to the turbine, 1 divided by S plus 3, and based on the pressure, how much the rotation is going to be, the torque is going to be taken, and then a generator is having 5 divided by S plus 1 times of value, then the actual speed, and give back the feedback here. Based on the terms, we can write the equation as G of S in the open loop transfer function, that is 500 divided by S plus 1, S plus 10, S plus 3. First, you have to do whatever the equation is given. First, you have to write the equation in terms of represent J omega equals to S. Therefore, if I represent here S into J omega, that is, then we'll be getting as 500 divided by J omega plus 1, J omega plus 10, J omega plus 3. Then go on multiplying take the complex conjugate part, and then go on multiplying, you'll be getting the equation of like this. Then find out what is the magnitude of that part, and also about the angle. In the previous case, what I explained about what is the magnitude and also about the phase and how to calculate of that part. After getting this, you have to go with a sketching of the Nyquist plot. First, you have to tell whether the magnitude is varying with respect to 0 to infinity based on the real and imaginary values. This is what here it is going for. This whole part is of a real, and this whole part is going to be a imaginary part. Then first equation of this part is going to be equals to 0. Then first, if it is 0 by anything, it's going to be 0. Anything by 0 is going to be equals to infinity, is going to be again equal to 0. These are like some methods you have to follow. Therefore, find out your omega 2, omega 3. you'll be getting 0, 6.5574 minus 6.5574. These are different frequencies you'll be getting. Based on the frequencies and what is the conditions you taken, you should follow those, and then the steps will be continuing. Then you'll be getting the in table. It's giving the all information for the real values and also for the imaginary values in terms of angle and also in terms of a magnitude. This is the values you'll be getting of. After getting the values, if you just go with the drawing part, you'll be getting the Nyquist diagram like this way, where the first path is going to be taken as from infinity. It will be varying towards a 0, and from 0 to infinity. Then the next path is going to be varying, observe here, from infinity towards the 0. Here 0 to infinity, from infinity to 0. This is how you will be getting the Nyquist diagram. In the same way, it's going on. This is about a theory way. When we go with the problematic part, problematic is a simple instructions we have to follow while writing in the program in our MATLAB. For Bode plot, first you have to mention the numerator part. Numerator is given as an input. You have to enter the numerator values. Then for denominator, give that write it as an input and enter the denominator values. Then you can take any of the function here. It's not that SYS only you have to take any system function, or else you can write any give as a G or H. You can give, then H is going to be equals to transfer function of numerator to the denominator. Then word of what is the word you've taken here? The same thing has to be represented here. Means the Bode plot will be drawing with respect to the transfer function. Then use of this part means it is displaying for the diagram. The Bode plot is going to be displayed. This is how you will be getting the Bode plot in a MATLAB. When you execute this, this represents a magnitude part, and this is going to be representing a phase part. When you click on a link of this blue color line, wherever you click, it will be showing the value of that part. Okay, when you are executing in a real part, we'll be going through that. This is about a Bode plot. In the same way, for the Nyquist plot, here the programming is very simple. Again, you have to go with the numerator part, that is input, enter the numerator, denominator part, give as an input, that is enter the denominator values. Then SYS or as any of the function you can write here, transfer function of numerator and denominator. Here it will be changing. Instead of Bode, you can write here as Nyquist. The spelling should be correct so that you will go with the Nyquist plot only. Of that transfer function SYS, then display of the Nyquist plot. You can write it any of the name, which one you want to give here. You can give Nyquist plot, or else you can write only Nyquist plot. It depends on yours. Therefore, after executing of this, you'll be getting a Nyquist diagram like this. The same example of what we taken in this case, the same almost is similar of this, only here it is taken. This is what a Nyquist plot. Observe here the -1 part. This will be showing whether it is a stable one or not. It's not enclosing with a -1, so we can tell that the system is going to be a stable one. This is about a Bode plot and Nyquist plot.